Alright, welcome back. My name is LUKAMA. I'm a student at NIT Rock Hill. So, after modeling this building, we assign loads. If we go to General, we go to Load and Definition, we assign these loads here, including the earthquake loads and the automated combination loads. Now, before we go to our next step, let us try to understand some basic things about analysis. Staad Pro, or let's just say in structural engineering, we analyze structures or buildings in two ways. Static analysis is one way. The other way is called dynamic analysis. So in static analysis, the system or the building and the boundary conditions do not depend on time. So in that case, what matters is just the intensity of the load. So we define the intensity here. Let's go. We define the intensity here. But in the other case of dynamic analysis, there is a time dependency. So what matters is the intensity of the load and the temporal distribution of the building. So in dynamic analysis, time is a variable that we need to consider. So in dynamic analysis, there's one analysis that we use to define those, or we use to analyze, called mode analysis. So mode analysis is a simple way to calculate the natural frequencies of your system, so you know which frequencies can be destructive and dangerous for it. Structures vibrate. If loads are applied to structures, let's say loads that depend on time, such as dynamic loads, these include earthquakes and everything, they depend on time. So when these structures are hit by those loads, they vibrate. They tend to move up and down like oscillations. So in order to know which frequencies are safe for that building, we need to know the natural frequencies of that building, which depend on the properties of the building and the self-weight of the building. So Staad Pro also can analyze dynamic analysis of structures using the mode analysis method. Now, in the case of Staad Pro, it analyzes the model properties of the structure using a method called the response spectrum analysis. This method is mainly used to determine the response of structures to random or time-dependent loading conditions such as earthquakes, wind loads, wave or current loads, jet engine thrust, and motor vibrations. That is what we do if we want to analyze the dynamic behavior of a structure. So how are we going to do this? We do this, let's now start the process. We do this by defining a load case here. So when you define a load case here, we add, remember this load case is called, it's a model load case. So we name it as mod load. So we name it as mod load. Model load. This is named as mod load, sorry. And then make sure here you put none. None. And then we add. When we add, and then we close. And then we go to this same mod load and we define it, we add. After doing that, since this mod load depends on dynamic loads, which in a structure depends on lateral loads, such as wind loads, earthquake loads. These loads act in X and Z direction, not Y direction. So what we do is that we change the direction here and we change the factor to a positive 1 because there's no self-weight here. So put it as 1. We add, and also in Z direction, positive 1. We add, then we close. After doing that, we go to this self-weight and we assign this load to the structure. So how do we assign that? We press here, we go to select beams parallel to X, because it's self-weight in the X direction, and then assign to selected beams. We assign yes, beams parallel to Z direction, select Z, everything's been selected, assign to selected beams, assign yes. After doing this now, let us add the frequency. So you go to mod load, add frequency. Let's save this. Add frequency, then model calculation. Don't press here, just leave it. Add. Okay. Once you've done this now, we can analyze the structure. So let's analyze. Go analysis, save. Okay, so you've seen we have 0 errors here. Let's view the output file. Results. So as you can see here, there are a lot of options: the Eigen solution, mass participation factors, total applied loads, and so forth and so on. So when you go to Eigen solution, this is the option where we see the frequency or the natural frequency of the structure. So per mode 1, there's this natural frequency 9.655 cycles per second. And then the period is also there, each mode. This is 0.10357 seconds, and accuracy is also there. Then each mode up to mode 6. So these are the frequencies that we're looking for, the natural frequencies of the structure. These are the periods. So in case the applied load or the lateral loads of the structure applied to the structure has got a frequency which are matching these frequencies, the building might fail. So we do not want these natural frequencies to equal the frequencies of the applied load. So after doing this, we can find that per each load case, this is load case 20, frequencies per mode 7, 8, 9, 10, their own frequency, then on periods, their more accuracy. We'll see what these modes mean later on. So we can go Eigen solution to frequency, period, accuracy. Mass participation factors, we can check X, Y, Z, the factors, the summation of them. And these are the static analysis results, displacements in centimeters, reaction forces, all these things. So now let's go to post-processing option and see what we have. Apply. Okay. So once we are here, these are the static analysis processes, results. Displacements, vertical reactions, animation. Sorry, let's first go to beams. So as you can see, we can see the bending moment diagrams. So bending moment diagrams here. We can see these are the shear force diagrams. We can go to forces. We can see the forces here. Stresses. You can see the stresses, as you can see, all the stresses. We'll go to graphs. So we can isolate a beam, and these graphs are here. So you see the bending moment graph, the shear force diagram graph. You see the bending moment graph. We can go to column, bending moment diagram, and shear force diagram are here. So each column, each member has been given the bending moment diagram and the shear force diagram. We can check them here. So this is the static analysis. Now let's go to the results of the dynamic analysis of the Staad Pro member. So we can go here and check. So what we see here, these are called modes. As you can see, this is mode shape 1. These are called mode shapes. So mode shapes represents the shape that the building would take when applied with dynamic loads. So we can change these mode shapes how? By doing this. Mode shape 1, mode shape 2, it changes. Mode shape 3, it changes. As you can see, it's same as change. We can increase the scale like this. Mode shape 4 changes. Mode shape 5, as you can see, this is how it is. Mode shape 6 changes. As you can see, this is how it is. So now, let's try to see what the animation will look like, how these will actually look like when the lateral loads are applied to it. So how will you go? We will go, when you check, these are the mode shapes, and these are the other mode shapes too. We'll go to animation. Let's go to animation first. Let's change the extra frames to, let's say, 70. Let's put post 70. Let's put post 70 mode, and then let's apply. As you can see, this is how it is. So this is how it would operate. We can actually go to loads and results and see how. So we can change, and each mode shape has got its own specific frequency. So if we change the frequency here, we put this, then we apply. Have you seen the orientation of the mode shape and its deformation changes? It's in this way. When we change to 9.82 haze, we apply. The orientation changes, as we can see. We go to 10.5 haze, apply. The orientation changes. So when these loads are applied, in this case earthquake loads, this is how the vibrations will cause this structure to deform. So this deformation will depend on the frequency, on the natural frequency of the structure. Let's go to 15.8 haze, apply. That's how it will look like. Let's go to 18.4, apply. That's how it will look like. Let's close this. So we can put them here. Mode 1, you can see the mode shape. So these are mode shapes of the structure that we've modeled here. Mode 1, you can apply. So this is the dynamic analysis of the structure, and this that we see here is a static analysis of the structure. So in static analysis, we can see that each member has got, let's say, the reaction fx, fy, fz, and the moments here. You can go to stresses. You can see them here. You can see them. Each building, we just select, and then each beam we can move across the column actually, and see the distance, and we can actually display the corner stresses at the corners there. And then we can check the graphs. We checked this already. Then we can move around. You can see the forces per beam. So if you select this beam, so these are the forces here. These are the axial forces, maximum bending moments, shear force moments. So this is the static analysis results. And the dynamic analysis, we can just go here and find out. Have you seen? These are the mode shapes. Thank you very much. This is LUKAMA from NIT Rokela.